little nervous about that class, but
Okay. Welcome everyone to a cozy, accessible introduction to AI and cloud technologies. My name is Jake Howes. I'm a research data scientist in Trax Data Science Lab. Back in September, you may have seen a campus-wide email go out saying that the Office of the Provost is excited to announce the creation of two new initiatives, the forming of the Provost's AI Committee and the AI Acceleration Program. Purpose of these initiatives include increasing the level of AI usage and literacy among faculty, staff, and students, as well as to help them take ideas for using Gen AI, and enable them using available cloud-based computing resources. Now, let's say that someone asked you right now, can you explain to me what Gen AI and cloud computing-based resources are? How would you be feeling? Confident in your ability to answer the question, or maybe more like our friend on the bottom right here? So if you're somewhere closer to option 2, then you are in the right place. Now, we are going to be covering a lot today. We're going to talk about the concept of big data, and we'll spend most of our time going through some major techniques and concepts of AI. And we'll finish with a brief overview of cloud computing. We'll be taking it nice and slow, and we'll spend most of our time focusing on main ideas rather than the technical details and caveats. There will be a few times when we'll dip a toe into more technical details. And if those parts aren't for you today, that's fine. Just focus on those broader ideas. And I have truly ridiculous, cozy stock images of fall throughout this presentation to help you stay relaxed and comfortable. So with that, let's begin by talking about big data. So before trying to figure out what big data means, I do think it's helpful to have some idea in your mind of what regular data are. So I have here various examples of more typical data sets that you might encounter and to analyze. So maybe you have survey data from 1,500 adults and these results need to be summarized. Or maybe symptom measurements were obtained from 200 participants in a treatment group and 200 in a control group, and the results of this clinical trial need to be analyzed. A university department may want to look at enrollment data for their programs over some period of time. Or a program may need to run analyses on their financial data. So these are all very traditional types of data sets, no big data here. On the other hand, here are some areas where you could start to encounter big data. Think about all the content posted to a social media platform over a month or a year or 5 years. All the data that are continually being transmitted and collected from home assistant devices and mobile devices like smartwatches and smartphones, logs of location data, performance data, heart rate measurements, sleep measurements, all of the transaction data, the browsing data, the product reviews of major online retailers that have nationwide market areas or larger. Our lab specifically works with large repositories of healthcare data where numerous healthcare systems contribute millions of records. And occasionally in the course of our analyses, we work with tables that get into billions of rows of data. Then, of course, there's the internet, all the publicly accessible content there, and we will be circling back to that one later. So I've, just for fun, one more here with some actual numbers, since the major businesses tend to not be so transparent about their data. So there are sensors all over the world continuously taking weather measurements, and similarly, energy systems have to be continuously monitored and measured for billing and regulatory purposes. So in 2018, the National Renewable Energy Laboratory and the Department of Energy launched the Open Energy Data Initiative with the idea of making big data on weather and energy openly available to the public to facilitate research. This particular data collection includes over 2,000 different data sets, and all these data sets together total over 2.6 petabytes of data. So just to give you some perspective, that much data is roughly equivalent to 26 billion Word documents, 520 million images, or 650 million song files. So when it comes to actually trying to define what this term big data means, it's actually not so simple. And this is because there's currently a lot of inconsistency in the way that different people use the term. So the more intuitive approach to defining it is to think about it at the data set level. That is, this data set is a big data set. Is that data set count as big data? So even with this approach, it's not as simple as a size cutoff, though, for how many gigabytes or terabytes or petabytes you need before it's big data. Instead, it's more about this idea that once a data set becomes too large or too complex to be effectively handled by the traditional methods you have for data storage, processing, and analysis, then you're entering into the territory of big data. And you'll need a different set of tools to really handle and make use of that data. For example, a lot of people rely heavily on Microsoft Excel to track and analyze their data. But Excel has a strict maximum limit on the size that a spreadsheet can be, not to mention how difficult it becomes to use Excel once you get into a spreadsheet with thousands of rows or columns. And touching on the complexity side, I can tell you, for example, Amazon's data is not stored in one enormous spreadsheet. Large organizations need more complex formats, distributed formats, to organize their data. So when data are stored in more complex ways, we also then need more sophisticated tools to make use of those data. And similarly, traditional statistical software, like your SPSS, your Stata, these were not designed for big data, nor were the traditional statistical tests that they were originally made to run. So many statistical tests start to lose utility even in the realm of thousands of data points. And it's not surprising, given that a lot of these statistical tests were developed before the era of big data. So that's one way to think about big data in terms of how big and complex a data set is. Another way that people use the term is not in reference to a given data set, but it's more as a field. This field that encompasses massive data sources and the emerging technologies and processes for dealing with those. So you may hear it talked about that way as well. So why did we start here by talking about big data today? The reason is it's really foundational for the other concepts that we will be talking about today. Part of what cloud computing is about is creating computing infrastructure that can handle big data. And then AI techniques are the way that we're harnessing the power of big data. So we'll get ready now to move into our AI topics. But before that, I want to check to see if we have any questions so far, and I'll give you a couple notes too. So we have the other members of TDSL here today as well. And some of them have more experience in some of the topics I'm talking about today than I do, so they may be helping with questions as well. And for our Zoom attendees, Peter is here and can relay questions to me that you drop in the chat. Or if you want to go on mic for your question, you can use the raise hand feature on Zoom, and Peter will be coordinating unmuting your mic so that you can talk. So if anyone have any questions they want to bring up at this point?
All good, Peter? Not getting anything on chat so far.
So moving into AI then. AI consists of the technologies that enable computers to perform tasks that somewhat mimic human abilities. And in broad terms, here are some of the things that we use AI for. A lot of AI is about getting the computer to generalize from examples. So we give it lots of examples of something to analyze. It tries to find the patterns in those examples, and then it can use those patterns to perform some task. So we'll get into more details about this process later on, but a lot of times that task is predicting an outcome based on what the computer has learned from the examples. Or other times we use AI to perform a classification task. This just means we're trying to teach the AI model to categorize our input. Like if we gave it model baggage scan images, if we gave the model baggage scan images, we could try to teach it to categorize each image as either contains threatening objects or doesn't contain threatening objects. And then, of course, another one we've all been hearing a lot about is using AI to summarize information or answer questions using human language. So this includes the chatbots, the digital assistants, the co-pilots that have been getting a lot of attention and keep popping up in more new places. And then another big use is computer vision. So this is where the computer learns to identify and track objects in a visual scene. And this can be done in static images or in video. And this can include applications like facial recognition, or I actually recently heard about an application that's almost the opposite. So they were using AI to scrub all information out of video that could be used to identify individuals. So here we're talking about AI broadly, but there are different kinds of AI. And this figure gives us a structure for thinking about these different concepts. So machine learning is one of the major kinds of AI. Deep learning is then an important subcategory of machine learning. And generative AI, or Gen AI, is a subset of applications of deep learning that often involve the concepts of natural language processing, often called NLP, and large language models, often called LLMs. So we'll talk about each one of these a little bit, starting with machine learning. Machine learning refers to the use of algorithms to learn from examples how to perform some task. Use of algorithms to learn from examples how to perform some task. And this may already start to sound familiar from some of the things I was talking about a minute ago, and this is going to keep coming up throughout the talk. So this idea that a computer or machine is learning from lots of examples, it tries to find patterns in those data, and if it is able to find meaningful patterns, which are captured in some sort of model, we then can use that model to do something useful. Now, I'll walk through a typical example of what this looks like. And here we will touch on some technical aspects, and that's just to give you some idea of how this all works. So you have some outcome that you want to predict. So here we're going to say that you're a real estate firm. You want some starting point for determining how much a house is worth when you're trying to decide what you're going to list that price. So your outcome is house price, and then you'll need whatever data you're going to use to try to predict that house price. So you have a bunch of features for each house that you're going to list that you think should be factored into determining the value of that house. So this will be things like square footage, number of bedrooms and bathrooms, lot size, year of construction, maybe neighborhood characteristics, etc. And then remember, in machine learning, we need examples to learn from. So this means full examples where you have the data for all these features, square footage, etc., but also the actual price of the house. So we need examples that have the outcome so the model can have a chance to learn the connection between all of the features and the outcome. And we'll take those full examples that you have, we'll divide those into two data sets. The first one we'll call the training data, and then the rest will go into what we call the test data. Then we'll select an algorithm that we want to use for this model. And there are many different types of algorithms out there. And the one that's going to work best will depend a lot on what your data look like and how you want to use your model. And sometimes people try and actually compare several algorithms to see which one ends up working best for their case. And we can think about the algorithm here as a set of knobs that can be adjusted. So when we then fit a model to the training data, we're taking those examples in the training data and letting the algorithm figure out how to adjust all those knobs, how to weight and use all of the features you give it to come up with a predicted house price that is as close as it can be to the actual house price. So just to say that again, the algorithm is using the training data to learn how to turn the input data into predicted outcomes that are close to the real outcomes. And then with the test data, we can ask the question, now that we've trained the model, which is that we've set all the knobs, we're not going to adjust them anymore. How good or how accurate are its predictions on a different set of examples that the model wasn't trained on? And we call this generalization. So just because a model can predict its specific training examples well, that doesn't necessarily mean it will make good predictions on new data. So we want to make sure a model can generalize beyond just the training data that it was trained on. And the test data set allows us to check this. So that's why we held that data out initially. And then if all goes well, at this point, you have a model which can be used to estimate how much a house is worth before you decide what price you're going to list it at. So you would give the model your input features and it would output a predicted price for you. And before we move on, I just want to show you a real example of machine learning so you can see what this looks like in a real context. So this study published last year compared satellite images from the year 2000 and the year 2020 in a region of North Cameroon. Part of the reason they chose this region is because it had been experiencing deforestation and agricultural expansion. Then they used machine learning to classify the pixels from these satellite images. So each pixel represents a little patch of land, and the model would categorize that pixel as cropland, forest, savanna, water, etc. Then the researchers were able to take these results and quantify how each category of land changed between 2000 and 2020. For example, they found a 7% loss of forested areas over that time. So land classification tasks like these are just one popular application of machine learning where the results can be used for urban planning, conservation planning, and agricultural monitoring. So that's a brief look at machine learning overall and some of the ways that people can use it. And with that, we'll go down to our next layer, which is deep learning. So deep learning is a type of machine learning and specifically uses a complex type of algorithm called a neural network to learn and to make its predictions. And these algorithms are called neural networks because their design is inspired by the way that neurons interact in a brain. The deep learning is a very powerful type of machine learning that can achieve impressive things, but it can also be quite expensive in terms of the compute resources that it requires and the amount of training data that it needs. Now, here we are going to get into a few details again, this time about how deep learning works, but these will build on what we talked about for machine learning. And again, if you don't get every detail, don't worry about it. I'm mainly going through this just to give you some idea of the complexity of deep learning models, which is what ultimately allows them to do the impressive things that they do. So recall our algorithm from before. We said it was like this series of adjustable knobs. In deep learning models, these are designed to use layers of computation, where now each one of these layers is like a series of adjustable knobs. And the knobs in one layer can connect to the knobs in the next layer in complex ways. So this particular diagram here is a very simple illustration of the general structure of a deep learning model. In reality, most layers would have a lot more knobs than this, and you can have many more layers than what is shown here. So the total number of adjustable knobs can get very high. We call these parameters. And we'll come back to this idea of large numbers of parameters later as well.
Sorry, is it okay if I can take a picture of that?
Yeah. So you can think about the input data as proceeding through these layers of adjustable knobs from left to right. And then each layer performs some transformation on the data until they reach the output layer. And so the layers have been designed so that by the time you get to the output layer, it's produced whatever the model is supposed to output. So some kind of prediction or classification. For example, if your model is supposed to classify the input as one of two possible categories, the output might just be a 0 or 1, indicating which category. Or for a fancier example, maybe your model is supposed to make a prediction in the form of an image. So the output layer would actually produce all of the pixel values of the predicted image. Because there are so many adjustable knobs in deep learning models, and they interact in such complex ways, you usually need very large amounts of training data so that the model can learn how to adjust all of these different things to get effective predictions. But just as before, we can use a set of test data to see how accurately the model is actually performing, how well it generalizes on new data after it's been trained on all of your examples. And as before, I do want to highlight a real example of deep learning in action. And this work was published earlier this year. The idea here is that before heart failure gets to the stage of causing noticeable problems, there are already structural changes happening in the heart. And these early changes can be detected with an echocardiogram, but by the time patients are having symptoms and the doctor would know to order the echo, they've already passed this early stage. So it would be beneficial if these early changes in the heart could be detected from something that patients get more commonly, like chest X-rays. And of course, it would be helpful if this detection could be automated or semi-automated. So this team was able to train a deep learning model to detect these early heart changes from chest X-rays. And the model detected these changes with higher accuracy than the comparison group of radiologists. So this study demonstrates a possibility of using a model like this for automated or semi-automated screening of signs of heart failure when a patient would go in to get an X-ray. So that's a quick introduction to deep learning and some of the ways that it can be applied. And then now we're ready to dive into our last layer of our AI figure, which is where we'll get to talk about the more cutting edge topics of generative AI, natural language processing, and large language models. The term generative AI is nicely straightforward. It refers to types of AI that can generate new content. And by generate here, we mean it's producing something more than a single value prediction, like we saw in our house price example, or more than a classification, like the example we looked at classifying satellite image pixels into land types. So instead, it's generating things like text, images, audio, music, or video. And remember, generative AI falls within deep learning in our AI figure. So generative AI uses deep learning to achieve these things. That is, it's using those complex neural networks we saw with all of the different layers in them. And then natural language processing refers to techniques that enable computers to process and or use human language. And this is involved in many forms of generative AI. So NLP is a broad concept, and it doesn't always involve generative AI and deep learning. But the more sophisticated types of NLP that you're likely to hear about or use do involve these techniques. So for example, think about those smart home devices and digital assistants that you can interact with by voice. They've used deep learning to learn how to understand human speech by training on huge numbers of examples. And they've also used deep learning to learn how to construct responses in the form of human language. And then this is where large language models come in as well. So LLMs are a specific category of NLP. And these are deep learning models that can interpret and generate human language. So again, NLP is a broader term for when you're having computers interact with human language in some way. And then the LLMs are a specific kind of NLP, which allow computers to communicate convincingly using human language. So contrast this for just a moment with how we've communicated with computers up until recently. So if you wanted to tell a computer to do something, you would either write it in a computer language, which is a programming language or code, or you would click around in an application that somebody else already wrote in a computer language. And this is because human language is astoundingly more complex than computer languages. So it wasn't feasible to enable computers to use natural human language until recently. But now deep learning is powerful enough to enable this. So LLMs are what power the cutting edge chat technologies that have exploded in popularity. And likewise, research into all the possible applications of LLMs has exploded. So I just got back from a health informatics conference with 2,000 plus attendees. And the theme that they chose for this year was generative AI and LLMs. So even just in that space, research using AI, NLP, and LLMs is proliferating. Now we're going to take a peek under the hood of an LLM, and we'll use Llama 3 as our example. This is a recent version of Meta's LLM, released in April of this year. As I mentioned, it uses deep learning. So we're dealing with those neural networks with layer after layer of the adjustable knobs or parameters. And in the case of the flagship version of Llama 3, it actually has 70 billion parameters. That's 70 billion of those adjustable knobs. But if you need a scaled back version, they also offer an 8 billion parameter version. And then the training process for the LLMs actually gets divided into two main stages. And as we said earlier, to figure out how to optimize such a huge number of adjustments, you need a massive amount of training data. And specifically for LLMs, you need text data. So where can you find enough text data to train a model that has 70 billion parameters? It turns out there's a lot of text on the internet. So the first stage of training is called pre-training. And this is the stage that's really doing the heavy lifting in these models. This is where the model is learning a vast amount of knowledge and how to generate language based on context. And I've heard one AI engineer describe this pre-training process as compression of the internet. So at this point, the model is kind of like a zip file of the internet that can talk. And then Llama 3 uses somewhere in the ballpark of 70 terabytes of text data for this pre-training stage. The second stage of training is called fine-tuning. And for this part, you generally need a lot of human prepared examples. Now, if you think about the pre-training stage as the model learning language and knowledge, you can think about the fine-tuning stage as the model learning how to use those to perform some task. So in the case of chatbots, the model is learning how to respond to prompts and produce nicely formatted answers to questions. Now, that's as far as I plan to go today on LLMs. But if you are interested to learn more, I'll just mention that we are considering doing future seminars, taking a deeper, more advanced look at specific topics in LLMs. So be on the lookout or get on our listserv to hear about those. And before we go on to cloud computing, which is our last topic, we'll take a moment again to pause here and see if there are any questions.
Yeah, I have a naive question. It seems that everything hinges on the data set that it learns from. And almost by definition, it has to be public domain data. Does that constrict how generalizable these AI models are if there's vast quantities of restricted data that they cannot access?
Yeah, you could argue that, well, you could certainly argue that the models are constrained by the data sets that they're built on. That's very true. And yeah, you could argue that their ability to generalize will be constrained to some degree by what specific data that they got trained on. And so for models of the size of LLMs, publicly available data like general internet data is going to be the main source that you have access to. I do know that when some of these large companies train their LLMs, they also go through a lot of work to clean and curate their data sets to try to filter out some junk or noise in the process. But you're only going to get such a detailed cleaning when it comes to 70 terabytes of data. Yeah, go ahead, Thomas.
There's a small distinct, you use the word public domain. And so there's two different types of public data. So there's publicly accessible data, like the New York Times is publicly accessible, but it's also copyrighted. And one of the thorny things that has been working its way through the courts is that pretty much all of the modern generation LLMs are trained on publicly available but copyrighted data. The volume of truly public domain data is significantly smaller because of just the way that copyright law works. So one issue that you do have that's current in the court system is trying to figure out where exactly some of these, especially the very large ones where they're not telling you what publicly available data they put into it, exactly where responsibility falls if your LLM spits out a perfect duplicate of a New York Times article.
I would actually say even more recently, one of the things that we've seen among some actors is willingness is maybe not the right word, but a strategy to potentially eschew public data altogether. So for instance, if you look at the family of companies owned or operated by Elon Musk, which ultimately now I would say he's trying to transition all of them towards sort of AI infrastructure with Grok. I mean, those family of companies own, probably the world's largest repository of combined like near and far space data with SpaceX, at least North American road mapping data with Tesla for fully automated driving or attempts to do it. And most recently, well, in addition to, presumably they own all of the information that was on Twitter before it became X, but additionally, whatever is on X. But I think most interesting now, he has sort of, Elon Musk specifically, has asked people, we're looking to train on healthcare data, so just send us your x-rays and we'll take a look at them, period. And people have done it. And so like, that's not publicly available data, that's private data. But, it's interesting for one, because healthcare data is typically pretty difficult to access, both because it's private, it's highly secure. When it's owned by an actual healthcare provider, it's governed by HIPAA. But if a patient is you own it, it is not governed by HIPAA. You can send that to whoever you want, although at that point, that person has no stated responsibility to do anything or not do anything with it or protect it or not protect it. And so even just this week, there's been an article in the New York Times about Elon Musk, but possibly other companies, maybe even less publicly, really looking to obtain private data and maybe even sensitive private data to expand some of their capabilities, and the lack of visibility and infrastructure we have to potentially manage that. I think generally, this is maybe now editorializing, but I think a lot of people generally are sort of stuck between the space of there's really potential benefits that come from a lot of tools, but there's also right now a lack of, I'd say, regulatory framework systematically to prevent really terrible either data abuses or ethics abuses of how things happen. which I don't know, I guess maybe that's the story of industry at large, but that's kind of, from my perspective, at least kind of where we're at with artificial intelligence.
I mean, I was thinking, I don't do this, but if, say you wanted to use AI for drug discovery, well, probably the relevant data is patented by some drug company. So whatever your AI model comes up with is probably not very useful.
But the other part of that is that fine tuning process, since that doesn't involve the same quantities of data, a lot of times when a company or someone wants to train an LLM to do some, more specific task than just chatting like that, they do have access to, a lot of private data that they can use in the fine tuning stage. And that has been a big limiting factor on some of the new research applications people have been pursuing with LLMs is, they have these base models that have been pre-trained already. So the models know about language and they can kind of chat. But then when they're trying to teach it to do a more focused, specific application, they can't find a large enough set of specific data or of high enough quality data to complete that second stage, the fine tuning, to then really get the results that generalize that they want.
Patents are actually a really great example of data that is public but protected. So the whole idea of the patent system is that, well, if the drug company is patenting this, they have to explain everything about it so that other people can duplicate it once the patent expires. So there's a whole lot of useful information in patents specifically. But yes, if you did drug discovery looking, through these patent databases, you might be infringing something if it's patent.
A couple of practical questions regarding machine learning models. How do you determine your partitioning of training versus your final or the test set? 2, I hear there's argument about whether or not you should pre-specify your input variables or just let the model identify those in real time. And then lastly, in terms of the number of parameters or knobs, is there like a standard or industry standard in terms of how many allow you to do what, or is just bigger, go big or go home, so to speak?
Okay, try to remember them in order. So
Sorry. So
Right, number,
partitioning,
training, test.
training versus test,
Yeah.
and then whether or not you should pre-specify your inputs.
So with the training versus test split, the techniques actually differ quite a bit depending on the size and type of machine learning model that you are using. So when you're using some of the more basic machine learning models, a lot of times we'll do these techniques called cross-validation, where you actually end up dividing up your data set multiple times. And you do that train test split over and over again using different combinations so that you get a chance to use every data point as a test data point at some point, and then it's a training in all of the other iterations. So those are really nice when your data set is not impractically large. But once you start getting into larger data sets, then a lot of times you can't really do cross-validation. You're more restricted to just like a training set and a test set. And when you do those, the way you divide it up can also depend on what the output of your model is supposed to be. So if it's a classification task specifically, you might want to try to ensure that you have the same distribution of outcome classes in both the training set and the test set to make sure that you're going to get the most comparable sort of results. And then in terms of pre-specifying your features, yeah, I know a lot of people do this in different ways. I think it is, it does kind of vary with the size of the models, again, and the complexity, where when you're using the smaller sorts of models, simpler ones, a lot of times you're specifying the data. So if you have a very specific input data set, you kind of know what all of the variables are you have to work with. And so you can specify them in that way. Although you can let the machine learning part figure out how to weight those, and maybe it'll end up dropping some of them out. But then when you get into the more complex stuff, and especially like the deep learning, it's going to do a lot under the hood in terms of figuring out what it's using and throwing out. And sometimes people use what are called unsupervised learning techniques as an initial stage just to figure out what their features are going to be. And again, that's a more machine learning approach just to figure out what features you're even going to use. So that kind of stuff becomes more common when you get into the bigger models. I don't know, do you all have anything to add to that?
This is a question. I read somewhere that, training and test division, you can expect a thumb rule of 70% training and 30% test data. How relevant is what I read? Is that a thumb rule that people use or?
It's a thumb rule that
A
people
thumb,
use,
okay.
yeah.
Okay,
A lot of times I've used 80-20 when I'm doing the sort of splits. But people, yeah, so if you're just doing those more kind of simple splits, or you're even going to do those multiple times for the cross-validation approach, yes, somewhere in the realm of like 70-30 to 90-10 are very popular. It's probably not going to make too huge of a difference.
My experience is that 80-20 is the most popular rule.
okay,
And some of it depends on where your scarcities are and where your abundances are. So in some cases, when you have a whole lot of data, but only some of it is very high quality, you may want to restrict your training set to a set that involves that high quality subset. And as you get to larger and larger data sets, and this goes into the big data changes things issue, training is computationally expensive. So when you have very, very large data sets, you can't afford to train on 80%. You may be able to only train on 2% at a time because the training process is much more computationally expensive than the testing process. And this is especially true if you're trying to use relatively traditional machine learning models on very large scale data. You simply can't go in there and expect to be able to train a random forest on 3 billion rows. But you can test that random forest on 3 billion rows pretty quickly.
I would actually say two things. So one, I had comments related to what Dave said, but they would take a long time to get through. So I'm gonna save those. But the other piece I would say is, and this is my opinion, I don't know if, the three of you agree with this, but I feel like it's more about justification of your methods than like a specific hard number. So like, when you write a manuscript and you put your methods into it, I think people are less focused on like, did they do 70-30? And it's more like they did 85-15, but did they have really strong rationale for why they did it empirically? Or like this was the model that they specified, or like cross-validation. They did 5-fold cross-fold validation instead of 10-fold, or they did 50-fold cross-fold validation. Like, I think it's less about a certain number, and it's more about like, what was the rationale for doing it? And is that rationale scientifically sound and sound within the context of the study?
Do we have anything on chat?
Oh, yes, thank you. Somebody asked specifically related to LLMs about energy and environmental impact. So what kind of energy and environmental impacts are part of utilizing LLMs? Are they very different at different levels of training? And once trained, do they sort of quote unquote pay back some of that energy or carbon cost?
Well, payback would be a very tricky idea to pin down here. So, it's pretty well known that the computational resources for doing all of the training of the big LLM models are just so extreme. So they require these very large data centers that are really just huge, and they're built just to be a huge data center. They draw massive amounts of power. So there's a huge energy consumption. not to mention the actual raw materials that go into building all the computing parts as well. So there are major environmental impacts, certainly for the training process for these big LLM models. But like Thomas was kind of talking about before, once you have a model trained, the inference process with it, the making predictions, just sort of running the model that you already have, a much lighter computational process. So every time you send a prompt to an LLM to get an answer to a question or something like that, that's a much, much smaller sort of resource draw than that initial training process. In terms of paying back, you might have to start forming arguments about whether, they're saving enough kind of resources, building efficiency in some ways by the information that you can get out of the models that they're making up for how many resources it took to create them. But that would be a very complicated question I can't tackle in much more detail today.
Yeah, it seems like you could have produced 100 tons of CO2 in some sort of training aspect. But then, for all you know, if the models were used to achieve fusion at room temperature, they should be saving an infinite number of, tons of CO2. I'm sure there are people out there that are attempting to measure it, but it's so challenging to quantify. The thing I don't know if anybody else knows this is, so yes, the training is crazy, right? Like affects state level power grids when OpenAI needs to train, or, individual companies are now looking at opening their own nuclear facilities to sort of have enough power to do some of their LLM training and things like that. But so it's trained. I don't have a good sense of how energy expensive is, say, like submitting an LLM query to an OpenAI server versus running, I don't know, a big complex neural network on your local laptop. I bet the LLM is still more environmentally expensive, but that's pure opinion, speculation.
I don't know. Anything else in chat?
Not right now.
Okay. So we'll go ahead and wrap up with a brief overview of cloud computing. So as I mentioned earlier, part of the relevance of cloud computing is in its creating access to the computing resources needed to handle all these big data and AI techniques. But the basic idea of cloud computing is quite simple. It's outsourcing your computing work to faraway computers, which you can then access and manage through the internet. So this is in contrast with traditional computing, where the computing work, that processing is being done on the actual computer that you're using, or a computer through a local network or on a local computing cluster, or really any computing equipment that your organization owns and maintains. In the IT world, they call this on-prem or on-premises computing. So if you've heard that term before, cloud computing is in contrast to on-prem computing. And on-prem computing is done on locally owned and operated equipment. Cloud computing is outsourced to remote computing equipment, which is generally owned and operated by a third party. So why would you want to pay to access someone else's computing systems through the internet rather than just paying for your own system? There are actually many potential advantages. For example, with cloud computing systems, you generally don't have to worry about installing software, installing the updates, installing security patches, backing up your data, other software maintenance tasks, and all the hardware maintenance. The cloud provider, that third party who owns and operates the computing system, is responsible for handling these things. Although I do want to emphasize my use of the word general on this slide. Not all of these things are true in all circumstances. But on top of those things, cloud computing promotes this model and market of specialization. So cloud providers specialize in maintaining advanced computing resources. That's their whole focus. And then you're paying them for a service that's in their area of specialization, so that you and your organization don't have to specialize in that area on top of whatever your main focus actually is. And we'll underscore the word advanced in there as well, in advanced computing resources. So at times, you may want to access much more advanced or expansive computing resources than you or your organization can feasibly own and operate. And this brings us to the idea of scalability. So this often goes along with this service model of computing. The idea here is that if you own and operate these systems yourself, you have to pay for them upfront, along with their continuous costs of maintenance and employing all the staff with all the needed expertise for this. But with a cloud service model, you don't have to pay for a whole system and staff. You just pay for what you use instead. So for example, you're going to pay more when you use more advanced resources, and you'll pay more when you use resources for longer amounts of time. And these pay-as-you-go models make cloud computing financially appealing for many organizations, although I have a note here as well, which is that currently it can be difficult to estimate what your total costs are going to look like with these models, because they're really an accumulation of micro billing. So it can be difficult to transition to these cloud service models with any assurance of how your costs are going to work out with respect to your actual computing needs. Now, to be clear, not all cloud computing is about fancy computing resources like massive data storage solutions and advanced processors. Cloud computing overall is a pretty broad concept. So for example, something as simple as Gmail is an example of cloud computing. And this one even happens to be free in the case of personal use. So here, Google is providing and maintaining the email servers and the software that you're using, then you can access these resources through your web browser. And of course, sometimes you might be using a Gmail app on your phone, but regardless, Google is taking on most of the computing responsibility, and you're just connecting to their systems through the internet. As I've mentioned, though, cloud computing is especially relevant in the areas of AI and data science more broadly. And in these areas, it is often about bigger, fancier tools, things like large-scale and efficient storage solutions, powerful processors, and advanced software for doing data science work. And lastly, I'll just share this figure. First, to give you an idea of the major players in the cloud computing market, but also to help clarify, in case you've heard terms like AWS and Azure before, and you assume they were different tools that do different things, that's not necessarily the case. Each of these providers has a lot of different tools, and often they have tools that do similar things. So the AWS Azure part is really just about who is providing the tools. UNC deals a lot with Microsoft, whose cloud systems go under the name of Azure. So you can see those on the second line here. So that's the ecosystem of cloud services that we tend to work in. But Amazon is the leader with their AWS platforms, which stands for Amazon Web Services. And Google has also been growing in the third position with Google Cloud. So now let's take a moment to summarize some of our main takeaways as we wrap up here. So big data refers to when data sets are too big for traditional tools and methods. And this occurs commonly when we're working with AI. AI includes a lot of techniques, and many of those techniques involve computers learning patterns from example data, which are then stored in models that can be used to perform some tasks. Complex deep learning models are what power LLMs, and these LLMs are a type of natural language processing that allows computers to communicate using human language. And then finally, cloud computing provides web-based access to computing resources that are generally managed by a third party. And cloud computing resources tend to be especially relevant to AI work as well. So with that, thank you all very much for your attention, and we'll open up for any final questions.
Can you remind me what the generative AI tool is that we on campus are supposed to be using?
Yeah, so that one's called Microsoft Copilot. And it's based on an LLM as well. It's got some extra tools built into it so that it can do things like image generation in addition to just, replying in language. Anything else in chat, Peter?
Yes. All right. We have a person that unmuted.
Can you hear me?
Yes, we can hear you.
Fabulous. So I don't know, I'm guessing that most of the people attending here are from the sciences side of the house. For those of us who are on the humanities and professional side of campus, there are a whole handful of us that are about to launch courses about, AI ethics, AI regulation, AI in media, AI in language, learning, right, all the different variations here. And I think for most of us who are about to, I'll speak for myself. For those of us who are about to launch these types of courses for our students, we can't do that without doing what you just did. So I guess my question is, you have to understand the technology to actually be able to talk about its impacts on your field, right? Are you all do you come in and guest lecture? Are you providing resources that we can use for that? Like when I go to teach my course in the spring, I'm envisioning an opening unit on what exactly is this and what does it do? And so you've given me a great place to start, but I'm wondering to what extent you or the committee has thought about helping to kind of ground these courses in beginning understandings so that then we can go on to talk about impacts, ethics.
Yeah, sure.
Makes sense?
Yeah, I think so. So the first thing I would point out is this link that I have listed on this slide. So these seminars that we do here, these are recorded, and after maybe like a week or so, sometimes we get them posted to this SharePoint site. So this SharePoint site is accessible to anyone within the UNC Chapel Hill community specifically. So this particular seminar should get posted on there as well. So it should be available to you and to students on campus. And if you have, and we also try to build out, other educational resources on this site over time as well. We don't have a lot specifically about LLMs at this point, although we might consider adding some more things in the future. But if you're interested in, kind of a more specific kind of guest presentation at some point, we can certainly talk about that. Obviously, we couldn't go around to every class in the university, but for particular cases, we could discuss, what we might be able to do. So my contact information is on the screen here if you need to get in touch with us about that. And we probably work with Peter here, who's the director of our program, to discuss that.
Yeah, I'll also just add, this is obviously a very big topic for everybody. And I'll only speak for sciences or biomedical sciences, but I don't think there's a day that goes by that I'm not talking about doing something or potentially doing something with LLMs with somebody. So, this is a really big area where Data Science Lab is working and it's going to continue to be working. And like JP said, we do already have 2 seminars up. I gave a seminar on ways that we in the lab sometimes use different AI applications as sort of research assistants. Thomas gave another talk on deploying large language models locally, specifically using Ollama. And so, I think this is going to be a pretty major thrust of at least some of our areas of work for a long time. So happy to talk and try and collaborate and support. I guess also convenient, I'll say 30% of the lab's focus is on things like education. So, it certainly makes sense for us to come out and try and support people on some of these topics.
Thank you.
See, we are at time. Are there any other things in the chat?
All right, currently.
All right, so we'll go ahead and wrap up. So thank you everyone for your attendance and your attention, and stay tuned for our future seminars. Thanks.